Good morning, everyone. So we're gonna continue with our topic 3, right? So this topic, as you have seen, is the first topic focusing on differential equations, okay, which are the stuff that you get when you try to model engineering or real-world problems, usually. Okay, so the broad overview is this, right? The broad overview is that, oh, by the way, I have already uploaded past year midterms, as you can see here, right, next site. I made the announcement yesterday, right? So you are strongly encouraged to try out the questions first, right, before I upload, okay, before I upload the final solutions, or maybe some, along with maybe some intermediate steps for you to assist your checking of the working, okay? So midterms, so this format is very similar to the format that you'll be getting this year, which in question 1 you have your MCQs. Okay, so MCQs is 20 marks in total, 2 marks each, right? So you can see the MCQs are kind of similar to your quiz 1 format, right? So just MCQ and then you just choose the correct answer. Okay, so then that will be for question 1. So then question 2 is on the, as you can see, this question is on linear equations, right? Linear algebra. So you can see the question quite similar to one of the tutorial questions that you have, okay? Which is on the modeling of the financial portfolio, trying to get some income and then subjected to some constraints. So the first part usually is the math modeling part, okay, then followed by the solving part. And then you can see that eigen decomposition, that means your eigenvalues, eigenvectors are also being tested, okay, so expected. And then question 3 is on your topic 3, which is on differential equations, okay. So the first part will be the modeling, right? So there is some engineering problem or real world problem, right, that is described in words, okay? And then you will have to know what to apply, right? It may inform you of the application, right? In this case, the conservation of heat energy, right? And then if you apply to the battery, in the EV here, then you will get this equation. So you're supposed to get this equation and that will warrant you 4 marks, okay? So certainly later today we will go through how to apply the conservation of energy, and then you will need to solve, okay, the differential equation in part A, okay, and then of course you can see that the answer has been given, and then you are just supposed to see if you can obtain the answer given here. Then after that, part C, usually they will give you some, it asks you what is the practical implication of some phenomena or some parameter, right, that you have to kind of explain logically, okay? That means this part is actually on the interpretation of your solution from part B, okay? So because part B, they give you the solution here, what, right? So you cannot say that you cannot analyze the solution, right? Maybe you can't solve to get this guy, but the solution has been given. So therefore you can analyze this, right, and then answer the question accordingly. So this is testing you on your interpretation, right, of the mathematical solution in the context of solving the actual problem, okay? Yep, so this will be the past year midterms, right? So certainly, I understand that your midterms is on the Monday, right?
Yes.
After next week.
22nd.
9 o'clock, 9 a.m. Yeah. So I heard that you have another paper next week, huh? Or Tuesday. That's good lah. So that means you still have quite a bit of days to study before your paper on Monday, right? Yeah, so maybe Friday, next Friday, we will have a non-compulsory consultation session. Next Friday. Can be online. You all prefer online or face-to-face? Online, okay. So we can do a online consultation, right? So hopefully after your paper, circuit design paper on Tuesday, you have some time to try out this paper, okay? And then if you cannot get the answers provided by then maybe you can attend the consultation to ask me, okay? Oh, anytime, like 10 a.m.? Or you prefer afternoon? Afternoon better, like maybe say 3 p.m., around there? Okay, so I'll set it on the afternoon. Yep, Monday exam. Monday exam is like, Monday the midterms is like you go to the LT. No, it's just like your quiz one. But of course you work out on the paper. You don't get to use your laptops or any electronic devices, okay? Yes. It means I won't upload the full solutions because I realize I shouldn't upload the full solutions. If I upload the full solutions, then I believe many of you will wait until you see the full solutions, then you go through the full solutions thinking that if you understand, you can do. That's the wrong approach. You have to do the question on your own. Then after that, you check against the solution. Probably maybe 3 p.m. Yeah. Okay. So what I'll do is that I'll give you the final solution, and maybe along the way, right, give you some of the intermediate steps for you to check. The consultation will continue until I have no questions. So maybe I would say expectedly not longer than 2 hours. You can check with me. Yeah. So you check against the solution provided before that day, before next Friday, right? And then if you realize that you cannot get the answer, then after that Friday you can ask me. Then I can go through in more detail. Okay? Yeah, so coming back to the lecture material, so topic 3, we are on the separation of variables. That's where we stopped. Okay? So effectively, it's just identifying. So after you model the problem, then after you get a differential equation. So then the differential equation, you have to identify what kind it is. Okay? The identification is important because if you cannot identify, then you probably cannot apply the correct solution approach. As you will see later on, there will be more and more solution approaches appearing, okay, for various kinds of differential equations. So the first kind that you will encounter is the usage on the separation of variables. So in this case, it's called a variable separable ODE, right, whereby on the right-hand side, okay, so because this is first order, so first order usually what they can do is just isolate the y prime term, isolate the rate of change term, and then throw the rest of the terms on the right-hand side. Now on the right-hand side, if you can see that you can separate the function of the unknown function y, in this case, multiply to another function of the input variable x, then we call it separable. Okay, so separable really easy to solve in the sense that you just separate the variables each on one side, and then you can just integrate both sides to get the answer. So therefore, separation of variables is not difficult, but the challenge could be in the integration process. Okay? Could be in the integration process. So therefore, you will have to revise your integration approaches in your Math 1. Yes. Okay, the integration wouldn't be very disgustingly challenging, but integration by substitution, integration by parts, all this you should know. Sine, cosine, sine, cosine maybe not so critical. Okay, can Anyway, I believe if you are able to do the tutorial questions along with the examples here, right? You can see the integration examples. We will just keep it to this kind of standard lah. Okay, won't be so tough. So therefore, we have gone through some examples here, right? So you can see that this is separable. 2x squared is one function, y is another function. So therefore, you use the separation of variables, integrate both sides. And then this part is really trying to tell you do not need to add, you need not add this constant of integration on the left-hand side. Reason being, you're just going to sum them up later on. Okay, that means you're going to integrate with the constant on the right hand side. So no need to waste time because you move terms here and there, maybe you make some mistakes. Okay, so this part, just in a nutshell, add the constant on the right hand side will do. Then, and on this part, right, okay, most of the time when you see the ln, or when you see the 1 over y and you see a ln of modulus y, so what it is trying to tell you is that typically after you exponentiate both sides, you can actually just directly remove the modular sign. Okay, but I say this typically, because it really also depends on what you have on the right hand side. Okay, so as long as you observe that after you exponentiate both sides, you have a constant multiplied to some function. And that constant is going to take care of the positive and negative y. Right? You can see the constant, right, is going to take care of whether the y is positive or negative. So which means to say that actually the modular sign can be removed directly. Okay? So this is the takeaway. Right? But I must say this, you have to also be careful because not all the time after you exponentiate, right, you will get this form. Because sometimes the constant can be like outside the expression, right? So therefore, you might encounter some of this in your tutorial questions. So then this is another question that we have gone through, okay? So you can see the integration by substitution here is being engaged, okay? So this is, I mean, it's quite easy to use the substitution, right? It's not difficult to make the substitution, right? But at least you have to be able to do it. Okay, that means at least you are familiarized with the integration process. So now we are going to move on to getting the particular solution. Okay, so whatever we have obtained here, you see a constant of integration here, right? In this case, I have put the integration constant as a. And then you also get another constant of integration here, a, right? So you notice that there is always a constant of integration in the function on the right. Okay? So because there is a constant, so that constant theoretically can be any number, right? But more realistically, we want this constant to satisfy a known condition. Okay, so we want that constant to satisfy a known condition of this solution. When I say known condition, I mean at some x, we know what is the value of y. Okay, and this is actually very practical. This is actually very practical. So if you recall back at the pandemic spread problem that we mentioned, right? Because we know that at day 0, you have one person being infected. Okay, so that is called an initial condition. And when we solve, right, we can actually make use of this condition. That means I, the total infected, at t equals to 0 equals to 1. Okay, so because usually in many problems we know the initial condition and we want to enforce that initial condition, so we can use that initial condition to find our constant of integration. Okay, so therefore, the general solution is one that contains the arbitrary constants, and there can be more than one constants, by the way, as you'll see later on for higher order ODEs. But what we want to do, right, is when we apply those initial conditions, we'll be able to solve for those constants and get the particular solution. Okay, so the particular solution is called particular, right, because it's particular to the given conditions that you must satisfy. Okay, so these conditions, as I mentioned, are usually called initial conditions or boundary conditions. Okay, so you'll get to deal with boundary conditions in Math 3, because they are usually more difficult to handle. Okay, so for this Math 2, we'll just be dealing with simple initial conditions. So this is the flow chart that we are going to apply when we solve an ODE. So given the ODE, you recognize the type, solve for the general solution, apply the initial or boundary conditions, and then obtain the particular solution. Okay? So in the event that if you are not given the initial or boundary conditions, you can at most only solve for the general solution. Okay? So you might get a question like that in your midterms as well. So, further example. So now you're supposed to solve this ODE below for its particular solution given the initial condition. So this problem is known as an initial value problem, where the conditions at one point is being given. Okay, so this is 1 point lah, right? What does this mean? This means that, right, if you were to plot the graph, okay, because let's say if you want to plot the solution, as you'll see later on, usually we need to plot out the solution after we have obtained, right, to inspect. So this is your y of x, this is your solution, and this is your input variable x. So y1 equals to 2 is called a point, right? So this is at x equals to 1, y must be equivalent to 2. Okay, so you can see it's exactly this point. So this point is called the initial condition, and therefore it is called an initial value problem. Okay, so this guy is actually right here. So later on you will see that in the general solution, you can actually vary the constant to get different curves. But because of this initial condition that you must satisfy, right, then that will lock the so-called family of curves onto this point. So much so that you only get one unique particular solution. So let's try to solve this now together. Okay? So once again, separation of variables, because this is separable. So you can see that if I were to just divide the y plus 1 throughout, I have a dy here, and then this is 1 over 2 minus x dx. So you can see it's separated already. Then you just integrate both sides after it's separated. Then you observe that this guy is really just ln of y plus 1. Okay, then as I mentioned, no need to add the constant because it's going to get grouped with the one on the right hand side. Then this guy, you have to be careful. Okay, this guy is actually what? Minus ln of 2 minus x, then plus c. Why is it minus? Because of the chain rule. If you differentiate ln 2 minus x, you're going to get 1 over 2 minus x. Then after that, because of minus x, so you got to chain rule. So you differentiate minus x, you get a minus 1. So therefore there's a minus in front. Okay? So then after that, right, what you want to do is to isolate the y term because that is your solution. Okay? So therefore you exponentiate both sides. So you're going to get y plus 1 modulus equals to, so when you exponentiate here, you have to be careful. Okay? Because there's a minus here, right? So therefore this minus can actually be brought up to the exponent. So hence this is actually ln 2 minus x to the power of minus 1. Okay, which is just 1 over 2 minus x. So then you exponentiate both sides. You notice that this must be e to the ln, right, of this. Okay, then plus c. But e to the plus c is just another constant. Let's say a lah. Okay, then a e to the ln. Can But e and ln, they are inverse functions, ma. So really it's just a times 2 minus x to the power of minus 1. Correct? So this a is just e to the c. So then after that, okay, so this expression, I can actually write it as, cos e to the ln, then I get this so-called exponent down. Then this guy, right, I can write it as a over 2 minus x, right? Because it's just reciprocal. So it's a over modulus of 2 minus x. So you observe that there is a modulus sign on both sides. Okay? But understand this. The modulus sign on both sides are a, but you have this a here, what? So the a will take care of the positive and negative of the left-hand side term. Will also take care of the positive and negative of this right-hand side term. So effectively, you can just remove the modulus sign. Okay? So y plus 1 equals to a over 2 minus x. Okay? So since a can take care of the modulus. Okay? So what I'm trying to say here is that, you see this modulus, even if it's plus minus, then this one plus minus. So I don't care whether this plus minus or this plus minus because it's going to just get reflected in a. Okay, as we have demonstrated for the earlier question. So therefore you just remove. So you can see you almost get an answer already. So the answer is really just y of x, right, equals to a over 2 minus x minus 1. So this guy is called the general solution, GS. Okay, because you see the a constant up there, so therefore it's a general solution. So after you have the general solution, as I mentioned, now because your initial condition is given, so it is implied that you must get the particular solution. So now you apply. So apply the initial condition. So this is your IC, yeah? Apply initial condition. So you're going to get y1, right? But y1 is just a over 2 minus 1. Minus 1. So you just sub in your function. Okay, where x equals to 1. Then this guy, it must be equivalent to 2, right? It's a given condition. So therefore, if you solve this, you notice that you can get a already. So a is just 3. So after you get a equals to 3, then all you need to do is to sub a into the general solution. So this one just sub into the general solution. And you get 3 over 2 minus x minus 1. So this is called your particular solution. So once you get a particular solution, you can actually check your graph. Okay, this guy must satisfy the initial condition. Okay, it must satisfy the initial condition. So what happens here is that you might observe that as your x increases after 1, let me see this. Oh, it's going to increase. And then it's not going to get past, okay. Okay, so the solution actually looks something like that. So there's an asymptote here. Yeah, so the solution actually looks something like that. How I know that it looks something like that? Because can see the function, right? 2 minus x. So if your x is approaching 2, right? Then this guy will be the denominator 2 minus x will get smaller and smaller. Okay? So and then because 2 minus something that is smaller than 2, this guy will be positive, right? Okay? So therefore it's going to increase. You see? Right? So certainly we can plot this. And you'll see that when your a is 3, it's going to satisfy this initial condition. So we can actually check in decimals. So you can see that y equals to 3 over 2 minus x, right? Minus 1. Okay? So you see this is our... So if this is a constant a, right? And your a can be any value. Because if you don't have an initial condition or boundary condition, then you cannot define this constant of integration. Okay? So that's why we call this a family of solutions, right? When your a is not defined. Okay? Meaning to say when your a is not so-called prescribed. Right? So it's a family of curves. But your a must be 3 in order to fulfill the initial condition at 2, 1. Okay? Or sorry, at 1, 2. So at x equals to 1, y equals to 2, right? You can see that at a equals to 3 is going to give you the initial point. Okay, that means your curve, your family of curves, right, now become only one unique solution curve. Okay, and this unique solution curve is going to satisfy this initial condition, the given one, when your a value is 3. Is that all right? Okay, so which is what we have just drawn here. Any questions with the solution approach? Yes. Sorry? Your 2 minus x, yes? Yeah. If it has a modulus. This 2 minus x, if it doesn't have a modulus, it's not going to affect. No. What I'm trying to say here is, right, as long as you have a constant, okay, so if you have a modulus here and if you have a modulus here, right, it doesn't affect your final solution. The reason is because, let's say you can see that this is modulus, right? Correct or not? So that means, so this is something like what? This is something like modulus of a function of y equals to a times modulus of another function of x, right? It is just like that, right? So you see what's going to happen. Now, this modulus sign means this f can be plus or minus. So therefore, plus or minus f of y equals to a multiplied by plus or minus g of x, right? Correct, right? So now you see what's happening. Now this can be plus or minus, this can be plus or minus, but this A is going to handle regardless of the signs here, right? You understand what I'm trying to say? Right? So this can be plus or minus, this can be plus or minus, doesn't matter, right? This A is going to handle it. Just like what we have demonstrated here. You see this part? So I say that, oh, this one modular sign. Then the y can be positive y, can be negative y. But you notice what happened? When this is a b, right? And this is a minus b, the b and minus b, they are just constant what? B is a constant, minus b is just another constant. So might as well I just let a general constant, an even more general constant a, right, to represent b or minus b. So the same occurrence will happen here. It doesn't matter this is plus or minus. This a can be minus a, can be plus a, but it's just a constant. Okay? Any other questions? Yep. Yeah. Yes. Yeah. Yes, because at x equals to 2 is an asymptote. You cannot have 2 minus 2 in the denominator. This one 2 minus 2, then you get undefined. So therefore, yeah, it's an asymptote, it never touches. Is that alright? Good. So I would recommend you all try this one out. Okay, but this is an ODE that you cannot isolate y of x. Not possible to isolate y of x. Okay, for reasons you will see as you solve. So what you need to do is just to get what we call the implicit solution. Implicit solution means the y terms cannot be isolated, so you can just put them together in like the left hand side of the equation or of the solution. Okay, so maybe this one you try for I think 10 minutes. Yeah, so I should mark attendance. Alexander, Aliyah, Emelina, Angelico, Sean, Brian, Chen Chang, well, I think he's not going to be here. Zhen Yi, Ivan, Yang Eng, Emilia, Erwin, Yanjing, Zhan Yang, Dongping, Noritetsu here, Xavier here, Zoe, Jordan, Kyla here, Kevin, Ken Leong, Chiara not here, Dawson here, Chen Ying, Jonathan, Kun Yong, Mac, Mikhail, Mohan, Azari, Danish, Irfan, Naya here, Bing Jie not here, Keng Hong, Zixuan, Fadila, Phoebe, Yan Heng, Sherwin, Benjamin, Raymond, Reese not here, Ruji Ratanalai, Jun Pang, Jerome, Sean, Justin, Habo, Ryan here, okay, Suhadi, Johans, Weiyan, Yichong, Tianzhen, Trisha, Yang Hong, right? Yang Hong, Shi Kang, Xingzhi, Zotet, Zoom PY, later. Alexander, right? So let's go through together. So you will observe that this is also separable, right? Because just y over 1 plus 3y cubed times cosine x. So if you reciprocate or reciprocal the y terms, you're going to get 1 plus 3y cubed divided by y, right? dy equals to cosine x dx. But this guy is just 1 over y, right? 1 over y plus 3y cubed divided by y. So it's just 3y squared. Then of course can integrate. Then this one you also integrate. So this integrate 1 over y is just ln modulus of y. Then plus you integrate this, you just get y cubed. Then that's equivalent to integrate cosine is sine. Because you can just check. Differentiate sine x, you get cosine x. So integrate cosine must be just sine. Then plus a c. So indeed, this is your general solution. Okay, because you can't do much already, right? The y and the y cube, you cannot factorize or isolate y in this form. So therefore now, you have to sub in the initial condition to get the C value here. Okay? So notice that the y must be 1. So you have a ln 1 plus 1 cube equals to sine 0 plus C. But ln 1 is 0. 1 cube is 1. Sine 0 is 0 plus C. So this goes to show that C equals to 1. So that means your particular solution should be when C equals to 1. Okay, but then if you look at the solution here, right, it doesn't have a modular sign here, so what's going on? I mean, you're almost getting the correct answer already. Okay, just that there's a minor detail, right? This is a modulus. There's no modulus here. Okay, so what's going on? Now, because in this case, right, you have to inspect the solution. Left-hand side equals to right-hand side, right? This is your solution. Now, but because sine x is only bounded between minus 1 to 1, this sine x will be bounded between minus 1 to 1. But you plus 1 what? Plus 1 means this whole thing is bounded from 0 to 2. Agree, right? So this goes to show that, right, your y cannot be positive, cannot be negative. This y value cannot be negative. Because if y is negative, then y cube is negative. Okay? And because y cube is growing faster than ln y. So therefore, in this case, you need this expression to be positive. Is that right? This expression must be positive. Okay? And if this expression must be positive, and you know that, right, when y cube is going to be bigger than ln y cube is always bigger than ln y. You can check, because if you were to plot y cube and ln y, you will see that y cube is always bigger than ln y. I mean x cube lah, let's compare x cube. See? Okay, the y cube graph is always above the ln y graph. Can see? Okay? So which means to say that this y cube cannot be negative. So when you have negative y, this y cube will be negative. Can? So therefore, this guy must be positive then. Since, yes? Oh. Okay, so when you integrate cosine is sine. Why? Because you must understand that differentiate sine is cosine. Is that right? Can? In fact, if you integrate sine, then you get minus cosine. Because you differentiate minus cosine, you get sine. Okay? Yeah? No, y can be negative if you look at this expression. Because y, if it's negative, you put inside the modular sign, it becomes positive what? So therefore the ln has, that's why every time you ln, when you integrate, right, when you ln, you have to put a modular sign. Because y can be both positive and negative, because the modulus will make it positive for the ln to be defined. Is that right? Can? So therefore, since ln y plus y cube has to be more than or equals to 0, and y cube is always more than ln y, so therefore you get ln y plus y cube equals to sine x plus 1. So therefore this will be your particular solution. Okay? So this one maybe we can write one more lah. Y is to be more than. Any questions? Any other questions? Okay, good. Yeah, so it doesn't matter if I put it in this form lah, doesn't matter. Okay, both are fine, right? Implicit form. Right, just this one, just move the sine x over. Hence now we are going to jump into another kind of first order ODE that you will be tested to solve. Okay, it's called the linear ODE. So a linear ODE is one that can be written in this general form. Okay, you notice the separable one. Separable is what? Separable is y prime equals to p of x times q of y ma. Okay, something like that. It's called separable lah, right? But not all the time you get separable ODE. So therefore there's another kind that conforms to this notation. Y prime plus some function of x times y equals to another function of x. So it's called a linear first order ODE. Okay, why is it called linear? Okay, the thing with linear here, right, means that It is linear because it can be written as a linear combination of y and its derivatives. Okay, so generally, a linear n-order ODE has this form. So it's always function of x times y, okay, plus another function of x times y prime, plus another function of x times y prime prime, and so on and so forth, okay, until the n derivative. Then equals to another function of x, standalone function of x on the right hand side. Okay, so this is linear. You notice or not? It's linear function of y, y prime prime, and so on and so forth. Okay? So therefore, if you can write it in this way, right? This is a linear function of y, y prime prime, and so on and so forth, until y to the n derivative. So this is called a linear ODE. Then of course, that begs the question, what is a non-linear ODE? So maybe we should give some examples. Okay, counter example. So non-linear. So examples are, because if you cannot write in the linear form, right, then it's not a linear ODE. Like 2y square plus y prime equals to maybe 1. Non-linear. Where's the non-linear? Y square, right? It is not a linear function of y and its derivatives because you have this y square term here. Non-linear. Okay, then another one, like for example, 3x times y prime. Okay, maybe times y. Y prime times y. Okay, so therefore this is also non-linear. Then maybe plus x equals to 2. So where is the non-linearity? It's the y prime times y. You cannot have such a term. Okay? Because linear function, right, means that the variables themselves must stand alone one. You see the y prime all by itself. You don't have like a square, or it's not multiplied by another term in y. Okay? So the non-linearity is the square. This is the problem. Okay, then the non-linearity here is the y prime times y. And you can have many more, infinite more. So I give you another non-linear function also can, like sine y prime, sine of y prime. Sine of y prime is a sine, it is a non-linear function of y prime, what? So obviously it's non-linear already. Okay, so sine y prime maybe plus y equals to 3x. So this is also non-linear. Okay, and you can give so many more. Okay, so as long as you don't have this form, right, as long as you don't have this form, you are having a non-linear ODE. So this is the linear equation. Any questions on the definition of linear and non-linear ODEs? Can Okay, good. So how do we solve this? Okay, before we go through the linear ODE solver, right, notice that if let's say your P is a constant, your P of x, right, is not a function of x, it's a constant, let's say A. Then Q of x is another constant, let's say B. Then you notice that the linear ODE can also be separable. Okay? Because in this case, you can just write it as y prime equals to b minus ay, just move the ay across. And then this is just a function of y. Okay? And therefore you get separable. You see, you can separate. Can But, of course, if let's say P and Q of x are not constants, or any one of them is not a constant, then you have to use another method of solving. Okay? So actually this method of solving is called the method of integrating factor. Okay, it looks complicated, but at the end of the day, it's very straightforward. It's in fact, I would say, even more straightforward than the separation of variables. Okay, let's see. Okay, see. So now you just define the integrating factor first. Okay, let's define the integrating factor, right, to be mu, right? So mu equals to e to the integral of p of x dx. So the p of x is this p of x. So let me make it super clear. You have to use the correct function. Okay, so this is your linear ODE. And this p of x is this p of x. is the same p of x. So now, if you define it this way, right, then integrate small p, let's say you get big P of x, okay? Integrate, just get another function, so let's call that big P of x. Now, you take this e to the big P of x, multiply to the ODE, okay? So if you multiply to the ODE, you're going to get, can you see, e to the big P of x times y prime, times y prime, then e to the big P of x times small p of x times y, the second term, equals to e to the big P of x times q of x, right? The term on the right hand side. Okay, no big deal, just multiply throughout. Then you notice something very interesting. This guy is, when you apply the product rule, this guy is the product rule differentiation of this guy. Correct or not? Because if you were to do product rule differentiation, what do? You hold the first term first, then you differentiate second term, then you get this one. You see, hold e, then differentiate y, get y prime, then plus. Then just now you hold e to the p of x already, what? So now you have to differentiate. So when you differentiate this guy, you get small p of x being chain rule out, differentiate big P, get small p, correct? So then the y of x, right, don't touch, just leave it. Okay? So that means this this left hand side, right, is this. But e to the big P of x is just your mu of x. You see mu of x. Okay, that's your integrating factor. Then you notice that on the right hand side is mu of x times q of x. Agree? So what is the solution? The solution is, look at this. This just differentiate this expression, get another expression. This one, to solve, right, you just integrate both sides, what? Correct or not? This one is d dx of this. So you integrate both sides, you get rid of this d dx. So therefore, integrate both sides, you get mu times y equals to integral of mu times q. So from here, integrate both sides. You are going to get mu times y equals to integral of mu times q dx. You see, because you integrate this d dx disappear, so therefore you're left with mu times y. Then what do you want? You want y, or y is your solution. So you just divide by mu throughout. There. So if you divide by mu throughout, you get this. So isn't this the solution? So in a nutshell, all you need to do to solve a linear first order ODE is just find the integrating factor first. Then just sub the integrating factor into this formula. This formula no change one. Okay, always the same. So just find integrating factor, sub inside, perform integration, that's it. Easy, Okay, so I'm going to demonstrate. So look at this, right? Is it linear? Yes. Okay, because y prime stand alone, then this y also stand alone, So therefore, what is the p of x? 2. Compare apple to apple. Okay, so p of x equals to 2. Then what's the q of x? Q of x must be this e x over 2. Okay, step 1. Find the integrating factor. So mu of x equals to e to the integrate p, which is just 2, dx. Integrate 2, just get 2x. So the integrating factor is e to the 2x. Step 1 done. Step 2, write down the solution, the general solution. So y of x is just 1 over e to the 2x. Integrate e to the 2x times q, e to the x over 2 dx. No objection, right? Now take note, this e to the 2x cannot cancel off with this e to the 2x. Okay, for super obvious reasons, because this is inside the integral. Okay, this function is not like some expression. Okay, and then I also forgot to mention, you notice that, right? I didn't put a plus c here. Okay, later then we address that. We solve the problem first, because that one is quite easy demonstration. So from here, what do you need to do? Integrate. So therefore, this expression, right? Your y of x is just e to the minus 2x times the integration of e to the 5 over 2x dx. Because 2 plus half is 5 over 2. But then you integrate e to the 5 over 2x is easy peasy, right? So it's just e to the minus 2x times 5 over 2, oh sorry, in this case 2 over 5, because you have to reciprocal. Reverse chain rule or substitution, e to the 5 over 2x. Then remember to put plus c now. Okay, we go and differentiate this. Right, if you differentiate this, right, you need to chain rule down the 5 over 2. Then the 5 over 2 will cancel with the 2 over 5. So therefore you get the integrand function here. Okay, so this one is just a check lah. If you want, you can, I mean I'll always do because easy to make mistakes. So you notice that you obtain the general solution already. So this is just equal to, so you multiply in lah. So 2/5 of e to the x over 2 plus c e minus 2x. So of course you want to leave it in this form is also totally fine. So this one is general solution because there is no initial condition being given. Any questions? Okay, so why is it that I didn't add a plus c? Because if you were to add, right, you will always cancel off later. See this one plus c. So by right you integrate to put plus c. Okay, but you put plus c here, you're going to get ae2x. A is a constant, right? Then this ae2x, you put the ae2x here, right? But you put an a here, then you have another a here. So you notice that it is always, this a will cancel with this a. So might as well don't put lah. This a will always cancel with this a. Okay? So no need to add. So no need plus c in mu of x. Okay? No need to do plus c in mu of x, because it's always cancel off later on. Any questions? Okay, this question. So I'm going to demonstrate again. Okay, now you have to be careful. The p of x happens when this is a y prime. So if this is not y prime stand alone, you got to make it stand alone. Okay? So which means that you should divide by 5 first, or else your p is not the correct p. So hence you get y prime plus 1 over 5 times y equals to 5 minus t. So then what is your p of x? This is your p of x. In this case, p of t. This is your q of t. Okay, because the independent variable changed from x to t now. So as usual, mu. So e to the integral of 1/5 dt. So this is e to the t over 5. No need to plus c. Then just sub the mu into the general formula. So y of t equals to integral. 1 over mu first. So I straight away write e to the minus t over 5. Okay? Then integrate e to the t over 5 times 5 minus t dt. So of course, this is what? Function of t times function of t. And you cannot possibly do substitution or do any simplification. So this calls for integration by parts. Okay, you need integration by parts, right? So recall that in Math 1, right, we should use integration by parts in tabular form because it's a lot faster. So by parts, you should choose u to be the function that you can differentiate away. So therefore 5 minus t. Then the dv, right, will be e to the t over 5. So what you do? Differentiate the u function until you get 0. Wrong. There shouldn't be a minus t here. Then integrate this. So if you integrate, right, you get 1 over 1 over 5. So you get 5. Integrate again, 25. Okay, so by parts, we call your Math 1. So now tie shoelace and put a plus minus plus. Okay? So therefore, you are going to get the expression which is plus 5 minus t times this 5e to the t over 5. Minus minus, so plus 25 e to the power of t over 5. Remember to put plus c, okay, because it's indefinite integral. So if you look at this expression, simplify, right, there's a 5 times 5. 5 times 5 plus 25, so become 50. So you have a 50 e to the t over 5. Then you have a minus 5t, agree? E to the t over 5, then plus c. Okay, then you multiply in. You notice that you're going to get 50 minus 5t, but don't forget the c, plus ce minus t over 5. So this is your general solution. Any objections? If not, apply boundary conditions or you apply the initial conditions. So you're going to get y at 0. Y at t equals to 0 is 50 plus 0 plus c times 0. Oh, sorry, c times 1. Because c e to the power 0. Okay? And therefore this guy is equivalent to 50. But this is just what? C equals to 0. So hence you have your particular solution. So y of t is just 50 minus 5t. So you can see integration by parts is being required. Do you have any questions? Okay? Can Okay, now you try this one. 5 minutes. Last question.
Yeah.
Right, so let's go through. So once again, you will need to put it in this form, if possible. So you can see a t prime here. The one with the prime is the function to solve for. So basically, you just divide by theta in this case. So hence you get t prime, right, minus 2 over theta times t equals to 5 theta. So therefore, you observe that the p of theta is minus 2 over theta. Because you have a plus here, then this is a minus. So then the q of theta is your 5 theta. So you have to recognize the p and q correctly. So therefore, the mu of theta, the integrating factor, will be e to the integrate of minus 2 over theta, d theta. But you integrate this is just e, the minus 2 can factorize out. Then you get ln theta, ln modulus theta. Okay, because you integrate 1 over theta ma. Then here, right, is just e to the ln of modulus of theta to the power of minus 2. It means there's a squaring here. So you square modulus, become positive also, right? So therefore, this is just e to the ln, inverse functions. So therefore, this is really just 1 over theta square. Okay? So then, what's the solution, the general solution? So the general solution is t of theta is 1 over mu. But 1 over mu is just theta square. Then integral 1 over theta square times 5 theta. 5 theta here, times your 5 theta d theta. Okay? So this is really just integrating 5 over theta. Okay? So when you integrate 5 over theta, you get 5, you're going to get 5 ln modulus theta plus c. So indeed, this is your general solution. And notice that you cannot remove this modular sign. Why? Because there is no constant in front of the function. This 5 is a fixed positive 5. It's not like a c or a or whatever here. Right? So you cannot handle this being positive or negative. Okay, the c is outside. So you're going to leave the modular sign in. Okay? Cannot anyhow remove. So therefore, from here, you apply initial conditions. So your t1 equals to, so theta is 1. So that will be 1 squared times 5 of ln 1 plus c. Then this guy got to be equivalent to 2. So if you solve, right, you're going to get c equals to 2. So because c equals to 2, then certainly the particular solution will be just replacing that c by 2. Any questions? Okay, so this is your particular solution. Okay, so now we are going to finish up this topic by looking at mathematical modeling in a more complete manner. So we have discussed, or we have looked at some examples from the systems of linear equations perspective, right, in topic 1, I believe. Okay, but mathematical modeling can also extend to using differential equations or deriving differential equations. Okay? So generally, the mathematical modeling process means the derivation of a set of equations that govern the behavior of the phenomenon or system being studied. Okay, later on we have a concrete example. So the equations can be from laws, formulas, theorems, can also be assumptions and observations. So these equations are called governing equations. Okay, and they are usually differential equations. Now, you can have ODEs or you can have PDEs, dependent on what is the function that you want to know. Is it a multivariable function which will give rise to PDEs, or is it just a single variable function that give rise to ODEs? Okay, so PDEs, this guy will be in Math 3. Okay, so now we are going to look at a concrete example. So this is generally the flow of mathematical modeling. So let's demonstrate this 8-step process by a concrete example. Okay, so the example that I'm going to give here is in the process of steel production. Okay, you might have seen videos before whereby there's a blacksmith, right? The blacksmith maybe forge a sword or forge a weapon or something. Then usually the steel is being heated up to red hot. Okay, looks like the picture shown here. So after it heats up to red hot, right, then the blacksmith might hit the sword a few times, or hit the steel a few times. Then after that, form the shape already, right? Then plunge into cold water. Okay, plunge into water, then all the steam come out. So why is it that the blacksmith forged the sword in this way? Okay, why does he plunge the sword into cold water? Because the rate of cooling will decide the properties, the mechanical properties of that steel. Okay, so in a sword, right, typically you want the sword to be very hard. You want a weapon to be very, very hard. Hard then can cut, right? Correct or not? So typically the material, the steel material needs to be hard. So therefore, in order to create a hard material, right, you need to do this process called rapid cooling or quenching. So therefore, they put the steel into the water. Then you can see that it is to cool the steel very fast. Can okay? So this is one mechanical property that we want. That is a very hard metal. But if you want the metal to be soft and ductile, such that it is malleable, okay? Because different mechanical systems, right? They require different kinds of materials. So sometimes you want hard, sometimes you want soft. So if you want to have a soft steel, then you cannot cool fast. You have to cool it very slowly. Okay? In fact, interestingly, it is possible that you want to create a very soft material, right? A very soft kind of steel. What you need to do is to put the steel in a furnace or in an oven such that it can be controlled cooling. You cool over a very long period of time. Okay, then it becomes a very soft material. Okay, for its users, for example. Right, let's say you are trying to make jewelry or something. Okay, then you want the steel, right, to be a bit softer so that you can work with it. Okay, to cast all the different shapes and whatnot. Okay, so what's important here is that the process called heat treatment affects the temperature function of time. So you want to know what is the temperature function of time for this particular material, in this case steel, such that you can control the material properties, the mechanical properties like hardness, ductility, toughness, etc. Okay? So you see our problem, right? Give us step 1. Identify the phenomena to model. So the modeling is to be applied to the cooling of the steel plate here. Okay, so that the steel producers is their thing lah, right? They need to model or they need to know how cooling is being applied to a steel plate such that the steel manufacturer, right, can manufacture a certain kind of steel with certain mechanical properties. Okay, and by the way, if you go and Google steel catalog, you will see all the different categories of steel like AISI 1036, AISI 1024, those kind. Okay? So the different numbers, AISI, different numbers, right? They actually define the different kinds of steel with different mechanical properties. Okay? So that's the first step, identify the phenomena. Then in order to model this phenomena, which is the cooling, right? What is the independent variable and the function that you need to know? Obviously, because you need to know cooling. So cooling means you need to know the temperature function. Okay, and because it's cooling, so that means you need to know the temperature function of time. You need to know how fast or how slow the temperature decreases with respect to time. So that's your second step. Okay, define the independent variable and the unknown function that you want to solve for. So then, because you want to solve for the temperature function, from what? So then you need to get the governing equation. So in this case, the governing equation is to apply the conservation of heat energy and Newton's law of cooling. Okay, so we're going to make some assumptions. And because your plate here is pretty thin, right? So if the plate is pretty thin, we can assume that the temperature to be uniform throughout the plate. Okay, why is that so? Because if the material here is not a thin plate, it's a thick piece of steel, that means outside on the surface or near the surface, it will cool faster and much faster as compared to the center of that material. Okay, so therefore in that respect, right, you should not be able to assume uniform temperature. Okay, but if this is thin enough, you can. So here's the conservation of energy. Conservation of energy, very simple. Conservation of heat energy. Heat energy in minus the heat energy out will be equivalent to the rate of change of heat energy within that material. Okay, so this is in watts. Q in and Q out, right, is in watts. So therefore, Q in, right, okay, so conservation of heat energy. So it's just rate of heat transferred in minus the rate of heat transferred out. So this is equivalent to the rate of change of heat energy of that material. Okay, let me write on the next line. I spell it better. So this is the conservation of heat energy. Very simple conservation law. Correct. Okay, so you can see here. So this is your Q in, rate of heat energy in. Then this is your Q out, rate of heat energy out. Then equals to dE dt. Okay, rate of change of heat energy of the material. But what is the energy of the material? Heat energy is given by mc times the temperature. M is the mass, C is the heat capacity, and then T is just the temperature. Okay, so because M and C are constants, M and C here, they are constants. So if they are constants, right, you cannot differentiate them. So you can just factorize out of the derivative. So therefore, it is really mc times rate of change of temperature. Okay, so now, in order to decide this expression, right, we got to decide what is Q in and Q out first. So in the cooling phenomena, there is no Q in. Cooling process, what? Heat is not being added to the material. That means the material, it has been heated up to red hot initially. Then after that, right, put in the surroundings, for example, to cool down. So this is a cooling process. So Q in is 0. Okay? Then what's Q out? Q out is your convective and radiation heat loss. Okay? Because it's being rested on like some platform, right, whereby airflow can occur. Natural convection and forced convection can occur. So therefore, there's going to be heat loss by convection as well as radiation. So this convective and radiative heat loss is governed by UAT minus TS. So let me write down. This guy is going to be your Q out. So Q out equals to UA T minus TS. So what is this? Now, this guy is called Newton's law of cooling. So U is just like some heat transfer coefficient. A is the exposed area of the steel plate. So you have a substance, right? You have more exposed area, then obviously you're going to lose more heat. Okay, the exposed area to the surroundings, to the cooling medium, right? If it increases, then you can obviously see that it's going to cause your Q out to increase as well. Okay, so then what's the heat transfer coefficient thing here? So this U depends, for example, is there airflow velocity or not? What is the airflow velocity? What is the medium that you use to cool the plate? If you use water, then this U will be a lot higher. If you use air, then the U will be a lot smaller. Okay, so therefore this is dependent. This heat transfer coefficient, right, depends on flow velocity, cooling medium, whether it is like air or water, okay, etc. Okay, but we don't care. We just say that, oh, if it cools faster, right, then we will have a bigger U. That means the cooling is more effective lah. Then we just have a bigger U. Okay, but in reality, the U actually is a engineering feat to be able to define that. Okay, which we will not delve into too much. Then this is just the area, exposed area. Of course, bigger area cool faster, what? That's why you have your heat sinks for your CPU and your GPU. Okay, it's all trying to increase the area exposed to the airflow. Then this T minus Ts. So T is the temperature of the plate, in this case, of the material. This Ts is your surrounding or cooling medium temperature. So there has to be a temperature difference, then you can do heat transfer. Can So make sense So you notice that dt is just T prime. So I'm just going to have this expression. But this expression, if I isolate T prime, I get a first order separable. Notice that this is separable. UA and M and C, they're just constants. Okay? Then T is the unknown function to solve for. Ts is a surrounding temperature of cooling medium, which is also constant. So therefore, right, if I let R to be UA over MC, so this R is just UA over MC. Because I don't want to keep on writing UA over MC, it's a hassle. So I just define R to be UA over MC. Okay? Then what is the differential equation? Simple. T prime equals to minus R times T minus Ts. Then this is separable, what? Okay? So because the ODE is separable, you can use separation of variables to solve. So this brings us to step 5. Because after you derive the governing equation, the ODEs or PDEs or whatever, right, you need to solve. So separable ODE, I will solve. Okay, but we will solve together in the tutorial question. Okay, this one solve. Okay, then you're going to get this expression. Right, we demonstrate in the tutorial. So after we solve the governing equations, right, for the function that you want to know, okay, the temperature function, then what do you need to do? You need to inspect your solution using logic or your experience or your intuition. Does the function make sense or not? Because if it doesn't make sense, then maybe your solution approach or your solution process got mistakes. Okay? Then whatever you plot out, right, should make sense. Initial condition given, let's say at time t equals to 0, you heat up the initial temperature of the plate is 900 degrees Celsius. Okay? So by right, it should satisfy the initial condition. Okay? Then you must have the trend correct also what? Because you are modeling the cooling of the steel plate, there is no heat increase, there is no heat being transferred in. So the heat is being lost by the plate. So by right, the temperature must drop. Correct? You see? Okay? So initially, when the temperature difference is large, the gradient here is steeper. So that means the cooling is faster. Why? Because look at your heat transfer. It is dependent, right, on the temperature difference between the material and the surroundings. So if the temperature difference is bigger, then by right, this T prime will be dropping faster. Meaning to say the temperature will be dropping faster. So the rate of change must be more negative. Make sense? So this is also correct. Look at the gradient here and look at the gradient here. Okay? Then you look at the long-term solution, the steady state response or steady state solution of the temperature. Look at the temperature. The temperature reaches close to the surrounding temperature after 8.3 hours. So this one like a bit too long. 8.3 hours then drop to close to the surrounding temperature. Is there a mistake? Then if you think that there seems to be a mistake, but you're also not sure, okay, then maybe you need to change the parameters, right? Change the parameters. So maybe you feel that, hey, this one 8.3 hours is a bit too long. Okay, maybe my heat transfer coefficient is too low. I need to increase my heat transfer coefficient, okay? So let's see what happens when you increase the heat transfer coefficient. Any guesses what is going to happen? If I increase this heat transfer coefficient, that means, for example, I turn on the fan, right? I blow the air more strongly across the steel plate. What do you think is going to happen? Cool faster, right? So by right, if I pull this towards the right, this slope is going to approach towards the left. Correct? Correct? Okay? So if I decrease the heat transfer coefficient, then obviously it should cool slower. So cool slower means the temperature drop more shallower. Understand that? Okay, so this is what we call parameter study or parametric study. That means you go and change the parameters. Okay, then maybe give you another example. What happens if I increase the heat capacity, the specific heat capacity of the material? Let's say this is not steel. Okay, another material with, let's say, for example, a bigger heat capacity. What do you think is going to happen to this curve? If I increase heat capacity of the material, this one will cool down slower. Very good. Okay, because if you increase the heat capacity, then it can store more heat. Then for the same amount of heat lost to the surroundings, right, the temperature is not going to drop as fast because it is storing a bigger amount of heat. So therefore, let's see what happens. Okay, see? If I increase the heat capacity, it is cooling more slowly. Understand? Okay? So therefore, I've demonstrated this process called parametric study. So in order to inspect your solution, you change the values of the parameters and make sure that as you change the parameters, right, the trend of the solution makes sense to you. Okay? But of course, this is only true, or this is only applicable when you have experience or when you have the intuition, right, associated with this phenomena. Okay? If you don't have, then really it's more of a guess. Okay? Because it depends on what phenomena that you are trying to model. Okay? So this is what we call the preliminary inspection of the solution using your logic or experience. And then by right, you will have to validate your solutions by comparison with experimental data. So if you work in a company, you would have already a bunch of data sets being collected. Okay, so what one can do is that you compare your model with the data sets that you have. Okay, so then if there's a discrepancy, right, then you have to ask yourself, can you accept that discrepancy or not? Okay, if you cannot accept, then you have to find out what causes the discrepancy and what is it that in your model you did not consider such that you have this discrepancy. Okay, this means your theoretical model didn't agree with the actual phenomena that closely. Okay, because notice that initially at high temperature, right, agrees pretty well. Okay, of course this is on the Newton's law of cooling, right, for a beaker of water. Okay, not for a steel plate. So you heat up the beaker of water to 100 degrees Celsius, allow it to cool down. Okay, but the model is similar to what we have there. But then how come this one got like discrepancy as time progresses? Very good. Very good. Okay, so now as you have time progressing, right, the temperature Ts being increased what? Because the heat is being transferred from the plate to the surrounding. So this Ts by right will increase as time goes by because it's getting heated up and heated up. So therefore Ts increases by right. Now this part caused by the surrounding temperature or the cooling medium temperature increasing. So if the surrounding temperature increases, then the T minus Ts decreases. So if the T minus Ts decreases, the Q out decreases. So if Q out decreases, then actually the actual temperature cannot drop so fast, which is what you observe. Okay? So the actual temperature drop more slowly. So real temperature drop more slowly than the theoretical temperature T of T. Because the line is T of T. This is from your model. But the actual temperature, yes, correct. You're correct to say that. So the surrounding temperature, okay, so after this one, will cool. Okay, but then the surrounding temperature, if it's heated up, right, then it will be higher than the theoretical surrounding temperature that you assume to be constant. So they will so-called go to a horizontal line, but the two horizontal lines may not be the same, may not be coincidental. Correct, it won't meet, but it will be a horizontal line, close to a horizontal line. Can okay? So certainly the increase of TS here is a real observation, and we are going to be able to handle this increase in TS in topic 5 or topic 6. Okay, so for now we just assume TS to be constant. We do the easy modeling first. Okay, then, okay, sorry for exceeding. Maybe just give me another 2 more minutes. Okay, so then finally, step 8 is the last step. So let's say you can accept your model, or if you cannot accept your model, you go and refine your model and then resolve again. Okay, so after the step 7, after you have validated and you're happy with your model function, right, then you can apply already to solve the actual problem. Okay, so what you can see here is actually the different kinds of material microstructures that one can get, right, based on different kinds of cooling, such that they change the rate of cooling for your temperature T of T. Okay, so if you get martensite, then actually this is a very hard material. Then if you want to get austenite, this is a very soft material. Okay, so this part of course is not so important, just trying to tell you that different kinds of microstructure will give you different kinds of material properties. Okay? Yeah, so with that, this is an example, concrete example of mathematical modeling. You will get many more examples in the tutorial questions. So this will be the end of topic 3, and we will test until topic 3 for your midterms. Okay? So this one, I maybe share with you guys a little bit on this guy called Jim Simons. Heard of him before? Correct. Okay, so this guy is a mathematician, right? And actually, he passed away, I think, just recently, like 2 years back. Okay, of course, he's a billionaire, right? So how did he become a billionaire? That's the interesting question. So what he did is he applied his mathematical knowledge to modeling of the financial markets, like the stock market. Okay, and he is super successful. Now, he's so successful that his fund returns 66% annualized before fees. That means you invest, let's say, $1,000 at the start of the year. By the end of the year, you got $1,660. That means 66% annualized. That's how scary it is. Over 30 years, 1988 to 2018, this is 30 years, you know. So for every year for that 30 years, he on average returns 66% annualized. So you can see the exponential growth in his wealth. Okay? And this is not trivial. Right? The legend that you know, Warren Buffett, his return is way less than 66%. Okay, but he's a fundamental investor. He look at the fundamentals of the company, right? Like the management, like whether the company has a so-called moat, in the sense that it is very difficult to replicate their business, etc. Okay, but this guy, Jim Simons, he doesn't care what the company does. He just models according to the math. Then the math tells him buy the company, and he buy. Okay, so therefore, mathematical modeling is very powerful, and it can also be very profitable if you apply correctly to tradable assets. Okay, tradable assets. Can So just to give you some hope here, right? As well as give you some motivation why we learn mathematical modeling. Okay, right? Okay, good. So I'm going to call it a day here. Right, then I'll see you on Friday for the tutorials. So please try them out. And sorry, I didn't manage to go through the quiz questions. So I'll be going through the quiz questions on Friday as well. Thank you.